Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
We're going to elaborate a little bit on last time, where we started talking about pivotal quantities as a method of estimating. So I think pivotal quantities, as you remember, are a quantity that depends on your sample but also on unknown parameters, which sounds useless, but it's not useless because it has a known distribution. Quantities to derive confidence intervals, okay, which is a special type of interval estimation. Okay? So a pivotal quantity, as you recall, that's a function of the sample and the unknown parameters, possibly the known ones as well. Which has a known distribution. And we've seen the first example of a known. Now, the known distribution might not be quite as simple as some of the distributions we've done, but it's generally it'll be something that we can analyze. And in terms of actually coming up with the confidence intervals, That's a matter of taking quantiles, and there's special tables that you'll be able to use to do that in the exam. But so the first example was if you had x1 to xn's that are IID normal, unknown mean, unknown variance. Not a problem. We saw last time that x bar, of course, has the distribution normal mu sigma squared divided by n. Independently of the sample variance has the distribution, a scaled form of chi squared n minus 1. The scaling is exactly sigma squared divided by n minus 1. It's chi squared n minus 1. So that's just a stretched version, and those are independent. And the conclusion was that if we do, well, let me go. Maybe the conclusion was a little bit quick at the last time, end of last time, so I'll do it a bit slower for you. X bar minus mu, of course, is so far these are in the realm of observable. X bar and s squared are observable. Once you start subtracting mu, it's no longer observable because it has the unknown in it, but it will help. So x bar minus mu has the distribution normal 0 sigma squared divided by n. X bar minus mu, if we divide that by sigma divided by square root of n, has the distribution normal 0, 1. Technically, you might consider that a pivotal quantity, but it's not one that we can easily solve for mu or sigma, and therefore it's a bit hard to work with that. So it's better because of the two unknowns in that. So it's better in that context to scale. So what we really want is, instead of sigma over root n, we'll have s over root n. So the corresponding thing that we'll be dividing by is s over sigma, and let me just write it this way: s squared times n minus 1 over sigma squared, right? We know that that has the distribution chi squared n minus 1. Okay. So net result, if I divide that, so s divided by sigma, that's of course the square root of the thing I just talked about, n minus 1 over sigma squared s squared. But I'd better get rid of the n minus 1. So that has the distribution chi squared n minus 1. If you'll forgive this, maybe this is an abuse of notation, but I'm just doing the scaling as a, it's the square, so it is what you get when you take a chi-squared distribution, divide by the number of degrees of freedom, and then take the square root. That's what s over sigma has. And those two things are, once again, those two are independent distributions. And therefore, x bar minus mu, what we're really after, s over root n, this is a nice thing because everything in it is observable, or the n is known. The only thing that's not observable in here is the mean. So this is very useful for confidence intervals for the mean. That is, by algebra, it's x bar minus mu divided by sigma over root n. That's the first thing we have. Divided by the second thing that we have, s over sigma. And that has the distribution that is, well, it has the distribution I'll write it this way: z divided by square root c over n minus 1, where z is normal 0, 1. So rather than square, I'll say that this has the same distribution. When I say equals brackets t, that means the distribution is the same. Since the top of that is a normal, the denominator has the distribution square root chi squared divided by its degrees of freedom is independent of c, which will be a chi squared degrees of freedom being n minus 1. Okay, so that has the same distribution as this, and this is the definition of a t n minus 1 distribution. A t distribution is a ratio, how you derive it, a normal on the numerator, on the bottom, a square root of a chi squared divided by its degrees of freedom. You might wonder why we divide by the degrees of freedom. It's not a, that makes, by the way, that makes the formulas more complicated. If you go through and calculate the density of a t distribution, which is a good exercise in the kind of transformations we've done, if you go through and calculate it, you'll find that it is made much more complicated by this extra factor dividing by degrees of freedom. So it's a sort of a nuisance factor. But there is a good reason for the nuisance factor, and it has to do with tables. When you're on an exam, you're going to be looking things up in normal tables and t tables. So I'll even get the... By the way, this is probably the tables I provided. Just some... I'll probably post these so you can see. So that's normal. That gives you very precise values of the normal. Because you didn't need tables on the mid-semester, but for the final you'll need to be able to do some confidence in intervals. Anyway, so the normal I give you vast amounts of detail. For the t distribution, I don't give you all the distribution, I only give you quantiles, which you'd be familiar with from first year. And if you only have quantiles, part of the problem is you can't, there's all these different degrees of freedom. Each of them is a different distribution. And you see they start skipping ones. You've got 30, 31, 32, 33, 44, and then infinity. Now, if you didn't put that square root n minus 1 in this chi-squared, you would not have a limiting distribution. It would become very weak and diffuse. Because if you're... actually, no, it would actually... Sorry, it's the opposite. It would concentrate towards the origin. So... okay. The point is that the tables are useful in that even if you don't have the exact degrees of freedom in this table, you can look for a nearby degree of freedom. It will be very similar. You see that those are quite similar whether you're 32 or 34. 33 can be confidently predicted to be about halfway between those two. That wouldn't work if the definition of t were any different. And for degrees of freedom greater than 38, you might as well just use a standard normal. Now let's just think about that. Why? That's effectively saying that a t infinity is the same as normal 0, 1. That's true. It's so much as, well, in the sense that the limit of a t distribution, in the sense of that we already talked about, the limiting distribution is normal 0, 1. Now, why is that the case? Well, if you think about a chi-squared c, that's a sum of n independent normals, or it's a sum of n minus 1 squared normals. Each normal, so each squared normal has expectation 1. Remember, you take normal 0, 1, variance 1, so the square of it has expected value 1. So, just to remind you in case you didn't know that, expected value of this chi-squared is n minus 1. And it's also, you can do this because chi-squared is of course gamma. The variance of c is 2n minus 1. So, whether by the law of large numbers or just by taking that variance, you see that the chi-squared value is very close to n minus 1 with an error that's of order square root n minus 1. So when you take c over n minus 1, that's effectively 1 for large n. With very high probability the denominator will be 1 for large n, near 1. Now that's not true for small n. And that's why the t distribution becomes very important when you're talking about small sample size. All of a sudden the t distribution is nothing like the normal, except for being symmetric. But it has much heavier tails than the normal if n is small. And that's because if n is small, you're thinking about a normal divided by something that could actually be quite small. The chi-squared variable, if the degrees of freedom is just 1 or 2 or 3, there's a decent chance that c is around 0. If that's the case, then the value of the t statistic blows up to something very large. If n is very large, then the chance of getting something near 0 is quite low. So, that's why t distributions are most important for inference when, particularly important when n is small, or n small. Now, that's not to say that they're totally unimportant for n large, but it is to say that the differences between, you can even see back in this t distribution table, the differences between the t quantile and the normal quantile become pretty much very small, except for extreme quantiles. So this quantile is the 10, when it says t 0.100, that's actually the 90% quantile, 90th percentile, because it says this particular table gives you the area to the right being 10%. So that's the 90th percentile. So you see the 90th percentile of t 34, 36, 38, very close to the 90th percentile of normal. But suddenly it's not actually so close when you're looking out at the 99.5 percentile. This is 2.7 quite consistently, and then it's 2.5. If you were to look at even worse quantiles, so if you were to look at very, very low values of alpha, very low significance levels, you'd find that t and normal are quite different, even for high n. So the the further into the tail you go, the higher n you need before it's approximately normal. So while this is true, so a more precise way of saying that is that t nu converges to normal 0, 1 in distribution as nu goes to infinity. Nu is a standard letter for the number of degrees of freedom. So while that's true, it's sort of the relative rate of convergence is a lot quicker relative to the size near the middle than it is at the end. So the t, the normal is this nice bell curve. That's normal. The t distribution has heavier tails. Now, even though it gets to sort of match the normal fairly closely in the middle, even though it does, the tails are slower to conform. So it's not like there's no point to t above a certain level. There's a point to the t distribution for all values, especially in theory, but in practice, you're often working with, 95% confidence intervals, and at that point, maybe t bigger than, nu bigger than 30, you stop worrying about the difference between t nu and normal. So that's, we haven't yet got to the confidence interval associated with that. We've just talked at the pivotal quantity. So to get a balanced, now remember a balanced confidence interval, it's not always symmetric. It's not always the same symmetric confidence interval. We want, the confidence interval will be a random interval, as I said, with a lower, should I call it left, right, or lower, upper? I can't remember what I did last time. Let's call it left, right. We want the left bound of that confidence interval, the probability that the, now what do I, okay, in this context I'm going to call it t, because that's of course exactly the t statistic. The probability that t is less than L, okay, I'm going to get to the statistic later. Let's talk about a balanced confidence interval for mu, be very concrete. So we're not interested in a confidence interval for the variance yet, we're just doing a confidence interval for the true mean of the sample. To get a balanced confidence interval, you want the probability that the true mean is way off the left end to be alpha over 2. Remember, we're talking about a confidence coefficient, often called 1 minus alpha. Very frequently, 1 minus alpha is 95%, alpha is 5%, but it could be higher confidence if you want. So you want probability of being off the left, alpha over 2, and probability of being off the right equal alpha over 2. Okay, that's balanced because there's equal chance on either side. Now that won't always be symmetric in general, but in this case it's symmetric because t distributions are symmetric distributions. So thus, to get this, use the known distribution of the pivotal quantity, which we're calling t. Quantity t, and particularly its quantiles, which in an exam you'll have to look up in a table. In R you can type it in and it's a command, but since we're doing most of these things on paper, I'll just say look up in a table. Okay. Use the known distribution of t and its quantiles. So typically I might call that if t nu comma 0, let's call it alpha over 2, it's the 1 minus alpha over 2 quantile of the t nu distribution. Now remember, 1 minus alpha over, I tend to, quantiles are by convention measured from the left. So 1 minus alpha over 2 means that the area over here is alpha over 2 area to the right of the quantile, t nu comma alpha over 2. Now you might wonder why I don't write 1 minus alpha over 2 there. Well, maybe it's just to save handwriting. So this will give me a number that is positive. This t distribution is of course centered at 0. Area to the right of the quantile t nu alpha over 2. And this is the t curve, not the normal curve. which has slightly heavier tails. Okay, then the probability that the absolute value of t is greater than t nu comma alpha over 2 is equal to alpha, of course. It's alpha over 2 is the area to the right, and alpha over 2 is also the area to the left of the reflection, t minus t nu comma alpha over 2. Okay? So, that doesn't look much like a reflection. So that's positive and negative at the same value. So then there's then the probability of being in the middle here is 1 minus alpha, okay, which is what we want. So the typical is within there, and we're just excluding the exceptional cases as the kind of write-off. So go through, substitute the formula for the pivotal quantity t, and solve for mu. Now, this is not going to be solving an equation, this is going to be solving an inequality, so you just be a little bit careful when you're doing that. And how do we do that? T, if we recall back to what we were talking about a moment ago, t is x bar minus mu divided by s over root n. Okay? I substitute that in, probability that okay, if I place that in there and then I cross multiply by s over root n, then I'll get the distance between x bar and mu. I encourage you to think of absolute value as giving you a distance between the two, x bar and mu, because that's the easiest way to think about it, is greater than t nu comma alpha over 2 times the estimated standard error. Estimated standard error is a fancy name for the denominator when you're doing that. So, in case you're wondering what I was talking about there, I would call that the estimated standard error. Standard error is different from standard deviation. Standard error is standard deviation of something, but not of the original observations. The original observations, of course, xi's, have standard deviation sigma, of course. And then x bar has standard deviation sigma over root n, but we often call it the standard error of the sample mean, because standard error in your mind reminds you to think, oh, this is not the standard deviation of the individual observations, xi, this is smaller, because when you average you get a smaller standard deviation. So we call that the true standard error of the mean, I guess you would say, is sigma divided by square root n. But the estimated standard error, you don't know the true one, the estimated standard error is s over root n. So that's why we call it that. So then that cross multiplies into this simple form is equal to alpha. And the probability, let's solve. Now, you can do that by pure algebra, but I prefer to just think logically, what does this mean? This is the distance between x bar and mu. So under this constraint, and I'm actually, if you'll forgive me, I'm going to switch that around and say the probability of being between these two areas is 1 minus alpha, because, you know, outside is alpha, between them is 1 minus alpha. And that'll allow me to express it in this range. Mu is between x bar minus t nu comma alpha over 2, which is the quantile, s over root n, and x bar plus t nu comma alpha over 2, s over root n. The probability of that is exactly 1 minus alpha. You may be surprised that we're still exact after all this, but the exactness relies on the fact that we assumed IID normals in the first place. And when you have IID normals, this big theorem allows us very precise control of what's going on. The mean is exactly a normal. The sample standard deviation, sample variance is exactly chi-squared times this constant. And so you have an exact t-distribution. So that is exact. So in the real world, perhaps you would consider this an approximate confidence interval. That's because your data to begin with might only be approximately normal. But if your data are exactly IID normal, then this is an exact t-confidence interval. Okay? So let's... So confidence interval is, we'll call it LR, where exactly L and R is as you expect. L is x bar minus t nu alpha over 2 s So you just, luckily all these things can be calculated. X bar and S from the sample, nu is known in advance, and T nu alpha over 2 is the quantile that you get from your sheet. So that's, hopefully I'm hoping that all this is familiar to you from first year statistics. So I want to do a second example, rather than just plugging in numbers for that, which I think you can do by yourself. Let's do a second example where the method still works, but it's not just a simple t distribution. It's going to involve talking about chi-squared distributions actually, and it won't be a symmetric confidence interval. It'll still be balanced, but not symmetric. So a balanced, but not symmetric. Not symmetric in the geometrical sense, confidence interval. And this is when we start talking about variance. So suppose we are interested in sigma squared, not mu, where, so in a sample, the sample is going to be the same as in the previous discussion, x1 up to xn, IID, normal, unknown mean, unknown variance. Now, this is, there's still an unknown mean and unknown variance. There would be a variant of this that you could use if you did know the mean, and then you wouldn't have to apply some resources to guessing the mean. Here, even though we will be guessing the mean, we can still then profitably ignore it, and it uses the same methodology. And so, to be clear, we're looking for a confidence interval for sigma squared, not mu. Okay? So, in a sample, x1 up to xn. Okay. So we know, reiterating, of course, normal mu sigma squared over n. Now that's kind of less interesting for us because mu is not known, and independent of s squared, sigma squared over n minus 1 chi squared n minus 1. So this is now the thing that is of greater interest. And you see that this s squared, luckily the distribution of that doesn't have a mu involvement. So we just go straight off the second one. We can actually ignore x bar. So x bar existed. Of course, x bar goes into the calculation of s squared. S squared is, as usual, by the way, in case anyone didn't know the calculation formula for s squared, it's worth remembering that. Sum of xi squared minus nx bar squared. That can be, this can be quicker than doing each xi minus x bar by itself, because then you have to square all these strange numbers that might not be integers. So that calculation formula is useful. So the s squared, we want a balanced confidence interval, so we apply the same procedure. Find the pivotal quantity. Okay? Now, s squared itself is not pivotal because the distribution is this distribution which has a scaling by sigma squared, and sigma squared is unknown. We want the pivotal quantity to have a known distribution, so I better get rid of that s squared. So it would be enough to talk about s squared divided by sigma squared. That is a pivotal quantity already. Just to make my life easier, I'm going to do s squared times n minus 1 divided by sigma squared. That will make my life easier because that will make it exactly equal to this distribution n chi squared n minus 1. And chi squared is one of the distributions where you have a table. In the exam, you'll have certainly normal, t, chi squared, and f. We'll talk about f in a moment. So chi squared, as you see, by the way, remember what I was talking about before. The expected value of chi squared increases as degrees of freedom increases. So the reason when you're doing the t that you divide by degrees of freedom is because otherwise you've got this wildly increasing chi squared value on the denominator. Okay, so let's use those. You'll notice on the chi squared distribution table, unlike the t distribution table which I showed you before, the t table only gives you the quantiles on the right-hand side. Okay, there's no need to give you the ones on the left-hand side because it's a symmetric curve. So if you wanted t.90, you take the negative of t.10. Now it's different for chi squared. They're still in this table using the convention that we represent this area that's to the right of it. So chi-squared 0.005 is right out in the right tail of the chi-squared. That's, it starts out, if degrees of freedom is 1, then the expected value is 1. So the right tail guys are out 5, 6, 7. The left tail guys are very near 0. You never get a negative number, of course, because the chi-squared is a positive distribution. So just note that convention. Now, we find the pivotal quantity has the distribution chi-squared n minus 1. And then what we're going to say is that the probability that that observed quantity s squared, the pivotal quantity, which is not observed, divided by s squared, sigma squared, is between two different quantiles of chi-squared, n minus 1, comma, alpha over 2. So this is the right, by convention, which I'm using in these tables, that's the right tail. So, and then but that will have area alpha over 2 on the right tail. On the left side, I'll have to do chi-squared n minus 1, comma 1 minus alpha over 2. Okay? So those are two quantiles, and unlike in the t case, they're not easily related to one another. Okay, so that equals exactly 1 minus alpha. This is the chance that it's in the happy middle. It's not off the deep end to one side, and it's not off the deep end to another side. I'll sketch. Remember that chi-squared is always a positive distribution, and for degrees of freedom 3 and higher, it always starts at the origin. Interesting fact is that chi-squared 1 is an exponential, and chi-squared 0 actually has an asymptote. Sorry, chi-squared 2 is an exponential, and chi-squared 1 actually has an asymptote. But chi-squared 3 and higher all look roughly like this, starting at 0. And then you have a left quantile and a right quantile. So once again, we're throwing away a bit of area, and this is the sensible region that you'll be in, that region 1 minus alpha of the time, so probably 95% of the time. Okay, and now the key thing is to solve for the unknown parameter. It's once again solving a inequality, not an equality. So you have to be a little bit careful about how you do that. I'm not going to be glib about it. Last time I just said effectively, you talk about the distance between, you see, that's what I was, it's very easy when you have something in this form, you just say, oh yes, the distance on the number line between x bar and mu is at most this. So that's the left endpoint x bar minus that, right endpoint x bar plus that. It's a bit harder when you're multiplying, or when you don't have something that's of this form, absolute x bar minus mu. So in that case, you just obey a little bit carefully. So if I took this, there are actually two inequalities that are true at once here. I solve that for sigma squared, okay? And you would get sigma squared has to be greater than a certain thing. The quantile chi-squared n minus 1, 1 minus alpha over 2, divided by s squared multiplied by n minus 1. Okay? And then separately from that, I'd have to take this inequality and solve that one for sigma squared. And when I solve that for sigma squared, I've got sigma squared. I've done something wrong already when I do this. Yeah. So this one was wrong. That was 1 over sigma squared greater than that. Okay. Forgive me. Okay, so just two steps. That means sigma squared is less than, if I take reciprocals of both sides, s squared n minus 1 divided by the quantile, I squared n minus 1, 1 minus alpha over 2. Okay, and then in this case, solving for sigma squared, hopefully in one blow at this point, I would say sigma squared is greater than a certain thing on the right-hand side, s squared n minus 1 divided by chi squared n minus 1 alpha over 2. Okay, so put it together. You put these together because both of those inequalities have to be true at the same time. And the CI, the confidence interval, the left endpoint of it. You see, the left endpoint is this one that came from the right-hand inequality. The left endpoint is s squared n minus 1 divided by the right-hand quantile, chi squared n minus 1 alpha over 2. And then the upper bound of the confidence interval is s squared n minus 1 divided by the lower quantile, chi squared n minus 1, comma, since it's just worth bearing in mind that you want to make sure you've got those in the right thing. Of course, those two have to be in that order because that's a lower number than that, so it's not too hard to see this. So that's what a balanced confidence interval for sigma squared is. Now, equally valid 1 minus alpha. Often we call it a 1 minus alpha confidence interval because it has confidence coefficient 1 minus alpha. So let's call it a balanced 1 minus, so that's like a 95% confidence interval. Equally valid 1 minus alpha confidence interval for sigma. Now, why is this equally valid? Because we know that, just reminding, the probability that sigma squared is between these two bounds, s squared n minus 1 divided by I squared n minus 1 alpha over 2, and s squared n minus 1 I squared n minus 1 comma 1 minus alpha over 2. You know that that probability is equal to 1 minus alpha. And so that probability is just by taking square roots. Once again, it's not going to be a symmetric interval, but it will still be a balanced interval. Sigma s itself has a certain distribution, which is effectively a square root of a chi-squared. But it doesn't matter because I can just take square roots of all of these are positive values. So it's the same to take square roots of everything in this inequality. And then I'd have s times a certain square root, n minus 1 divided by I squared n minus 1 comma alpha over 2. You might wonder why I leave that chi-squared, because you're going to be getting that from a table. So you're not given the values for the chi. If the chi distribution is a square root of a chi-squared, then you're not given values for chi. So you might as well just use the quantiles for chi-squared. Less than s times square root of n minus 1 divided by chi squared n minus 1 comma 1 minus alpha over 2. Okay. So that would be your. So those two would give the bounds of your confidence interval for sigma. So once again, it comes down to pivotal quantities. Let's do one more of those, and I think it will actually. Now I'm going to get into the two-sample world. We've done confidence intervals for mean of a single sample, and we've done confidence intervals for the variance of a single sample, if you ignore the mean. Now, I guess one thing to note about confidence intervals, because they're tied up with probabilities, you can't say that both of those two confidence intervals are both true at once with probability 95%. The probability will go down when you assert more things. So I guess you could say that if mu is 95% likely to land in a certain interval, and if sigma squared is 95% likely to land in another interval, if you want to assert those at the same time, it's fair to say that the probability is at least 90%. Right? Because the chance of lying outside is 5. It's at most 10% chance of an error. But if you're asserting three things at once, then it might, the probability goes down accordingly. So that's just one thing to be aware of. If you compound things that you have certain confidence of, the level of confidence can go down. Okay, so that's also the motivation for things like ANOVA when you're comparing three samples at once. You don't just want to do pairwise comparison of A versus B, A versus C, and B versus C, because you have three comparisons, you get 3 times the error rate. So there are other ways of getting around that with ANOVA. Okay, but let's talk now about two independent samples. And this is pretty much the theory behind independent sample t-tests, and it's also pretty much the same as the case of ANOVA, where you have two samples, but we'll get to that later. So if we have x, for the moment, but here I'm not going to assume the same variance at the moment. So I'm going to have a sample x1 up to xn that come IID from a certain distribution normal mu sigma squared. And we're going to assume that we have another sample y1 up to ym. Doesn't have to have the same number of observations, IID from a distribution normal. I normally don't like subscripts, but here it seems sensible to have subscripts. Mu x sigma x squared, and mu y sigma y squared. So that's just to differentiate the two means and the two variances, which may be the same, they may be different. As we know, and then because they're independent samples, I want you to know that everything in the x's is independent of everything in the y's. So that means you have, by the theorem that we talked about last time, we have two independent copies, and each of them has the properties that we were talking about. We get four independent summary statistics, let's call it. I like the word summary statistics because the mean and the variance are the two most important summaries of a sample. For any basic inference you want to do about normal samples, effectively knowing the mean and the variance will be enough. So the four all mutually independent summary statistics are x bar, which are, you know, sum of the xi's divided by n, sum of 1 to n, so I have n. S squared, I'll have to call it s squared x because I'm going to have two sample variances. Sum I equals 1 to n xi minus x bar squared divided by n minus 1. Y bar, so we know that those are independent within the world of the x's, that was our theorem. And we know that within the world of the y's, sum I equals 1 to m, because there are m y's, y I over n, and s squared y are independent, sum I equals 1 to m of yi minus y bar squared divided by, sorry, and that shouldn't have been divided by n, that should have been divided by m, and here m minus 1. So all of those, now I'll just put all of these independent signs. But really, when you're talking, it's not just pairwise. It's all four of them have nothing to do with one another. Four mutually independent summary statistics. Okay? And once we have those four mutually independent summary statistics, we can start coming up with pivotal quantities for things we might want to test. So if it's just to do with the x's, we already know how to do it. We know about x bar minus mu divided by s over root n. If it's just to do with the y's, we know about y bar minus nu divided by x squared over n. Now, I just want to, there's a few cases that we have to do. So this is the baby case, but just to show you what is easy. So this is kind of the baby case. If sigma squared x and sigma squared y are known, okay, that makes it easier to come up with a pivotal quantity. I'm going to call it z for kind of obvious reasons. Z is going to be what happens if I okay, so this goes under the heading difference of means. You might later be interested in the variances, but for the moment we're going to imagine we're interested in the difference of means. If you just want the individual mean, you don't need two sample theories. If we want the difference of means, then obviously a point estimate for that is x bar, whose expected value is mu x, and minus y bar, whose expected value is mu y. Then I have to divide by the appropriate standard error. Standard error, it's easy to calculate. Standard deviation x bar is sigma squared x over n, and this is sigma squared y over m. So you add those together. Independent samples, you add the variance. So that's square root sigma squared x divided by n plus sigma squared y divided by n. Okay? So clearly that has a distribution normal 0, 1. Now you can use that to find a confidence interval. It would be easy. So your confidence interval, to continue from that, is mu x minus mu y. So this would be a 1 minus alpha confidence interval for mu x minus mu y. An exact one is, the point estimate is x bar minus y bar. Now, to save myself writing both of them, I'm going to do plus or minus. It's obviously symmetric because the normal is a symmetric distribution. This balanced symmetric confidence interval will have z alpha over 2. That's z alpha over 2. In the most example we're familiar with, you'd remember that 1.96. If alpha is 5%, this is 1.96. So that's an easy one to remember. Times the standard error. Standard error, of course, does involve the two sample sizes and the two samples. So this is kind of a cop-out because if you know it, it's easy. Okay, so that's if the sigma squared and sigma squared y are unknown. So if sigma squared x and sigma squared y are unknown, but assumed to be equal. Now this is definitely an assumption, but in some cases it's a perfectly valid assumption, especially if you know that the error is due to a certain environmental noise. Like you have two populations, you know the error is just due to environmental noise, and you know that's the same for both populations. That might be a very reasonable assumption. It's not like we're already not making assumptions. We've made assumptions that there are two populations that are IAB normal. So why not throw in one more assumption? The upshot of doing this nice assumption is you get a very nice pivotal quantity. And I want to show you how you get this pivotal quantity. X bar minus y bar, so that has a certain normal distribution, divided by square root, well, I'm going to call it SP. You'd be familiar with it from first year. Square root 1 over n plus 1 over m. Square root 1 over n plus 1 over m. And that has a distribution t, exact, n plus m minus 2, where s squared pooled, so P stands for pooled, you have to pool it in the right quantity. S squared x times n minus 1 plus s squared y times m minus 1. So in other words, you're getting rid of those denominators that already existed in the degree of freedom, and then you make it a weighted average, so n minus 1 plus n minus 1. A quicker way of writing n minus 1 plus m minus 1 is to write n plus n minus 2. Is the pooled sample variance. And we just need to think about this. The pooled sample variance, just think about that. Those two are both independent, and they're both scaled chi-squareds. Sigma squared x is scaled chi-squared. It's got this factor of n minus 1, sorry, sigma squared over n minus 1. And this is scaled by a factor sigma squared over n minus 1. Since we've assumed that sigma squared and sigma x squared and sigma y squared are the same, assumed to be equal, then s squared p has the distribution. You can just follow through, let's say, chi squared n minus 1 divided by sigma squared. You see, I've got rid of the factor of n minus 1 and the, sigma squared chi squared n minus 1. I got rid of the denominator of n minus 1 there. Plus sigma squared chi squared m minus 1 divided by a denominator of n plus m minus 2. Okay? And then I want you to, what is the distribution? That guy and that guy were independent. Does anyone know what happens when I add up a chi squared with 1 degree of freedom, n minus 1, and add another independent chi squared with m minus 1 degree of freedom? What happens? Remember, chi squared n minus 1, that's nothing other than n minus 1 squared standard normals added together, independent. And this is m minus 1 squared standard normals added together, independent. So when I add the two of those together, I get n minus 1 plus m minus 1 squared standard normals, all independent, added together. It just follows from the definition. Or you can go through all that stuff I said about gamma distributions. You add the shape parameters. So this is exactly the same distribution as sigma squared over n plus m minus 2, chi squared n plus m minus 2. So key fact is that t, as I said, has the distribution t n plus m minus 2. Now that is an exact distribution under the assumption of equality. I want to give you the case without proof. So everything in that we've pretty much proved. So that's an exact fact that's not proved. So if no equality, sigma squared x, sigma squared y, assume. Now, that's to say, it's not to say we assume they're not equal, it's just to say we don't assume anything is the case, then no longer is it useful to pool the variance, because S squared P is to estimate sigma squared well. If sigma squared doesn't exist, if there's no common variance, there's no point estimating. So what you do is you do instead, this is T, and I'll just put a little